Um, Hello? Whatever. Oh. But this one, test. All right, that's a little better. Okay, good afternoon, everybody. Hopefully this thing will disappear eventually. Oh, really annoying that it's doing that. See if I can, oh, it's gone. Oh, no, it's not. I lied. Let's leave it the same as system. Okay, so just a quick announcement about homework. So homework 2 has been posted. I think almost everyone has turned in their homework at this point. Homework 1, so I'll have it graded over the weekend, hopefully back by next Tuesday. Oh, will this go away or not? Stupid computer. All right, let's see if that's it. Okay, so just a couple of notes about homework 2, so just some food for thought. This is a question or a problem about thermal equilibrium. It's a you'll open the problem set if you haven't already. You'll realize, oh my god, it's like dangerous, and most of it is review. Okay, and the problem set, the kind of work that you're doing is very different kind of by the last one. Derivation, calculus, and more statistics. So I'm sorry, guys. The idea is about testing the idea of thermal equilibrium. And let's just remember what thermal equilibrium means. It's very, very simple definition. It means that whatever sample you're looking at has a well-defined temperature. You can define, in this case, the distribution of molecules in this mixture that you're looking at in this problem set. That mixture, the relative abundances are set by the Boltzmann distribution at the same temperature. So what that problem is looking, as you'll see, is looking at a sample in the gas phase, using real experimental data that I took in my PhD, of a molecule that's flexible. And so it's a molecule that can have different conformers, different orientations that are all stable. And the question is to look at the relative abundance of these conformers, all of which have different energy, relative energy, some are more stable than others, to see if the distribution is thermal, meaning that it has a temperature that defines the distribution. We use linear regression to do this. And the problem works through the linear regression, how you come up with a linear expression to relate abundance to temperature. You can use Excel or Eagle or any sort of statistics package you want to do the linear regression. And then most of the data is, most of the workup, the problem says mostly just analyzing the regression results. If you're comfortable doing linear regressions, this problem set doesn't take that long. It's mostly just, and most of the analysis that you have to do is looking at differences in energy, subtraction, arithmetic. There's really not very much complicated math. The most complicated thing you have to do is take a log, and then do linear regression. Get your pick. And please make sure to read the intro carefully. It does go through the set up the experiment for you, set the stage for the problem very comprehensively. So make sure to read it. That's all I have to say about that for now. So let's see if this computer will behave today. It's really annoying. Okay. So let's go back to where we were last class. Let me pull. And we were in the middle of a discussion about intermolecular interactions. I am going to leave this. And let's see if I can tell it to shut up. Okay. Well, we'll have to just deal with that.
Change it. Oh no, it's changed the speed.
It's just doing it on its own. Let's see if it stops.
I don't think it really matters which speakers.
I don't want it to use speakers at all. I just want it to stop telling me to do that.
Just turn the volume up.
That's exactly what I've done. Yeah, sorry. No, you have the right idea. Just the computer does not. Oh, that's whatever I did worked. Okay, let's just hope that stays. Okay, so let me just go back to motivate our discussion, right? The idea was to consider what makes a gas not ideal. And does the ideal gas law actually valid? And I hope I convinced you last class that in some sense it is not a valid approximation. Let me give you an example. Here we looked at how the volume of a gas deviates as a function of pressure at constant moles. Right? So you put in 1 mole in a liter container, and you measure at an atmosphere, a mole, how much volume does it fill? Or you could say I have a liter and I put a mole in there and I set the pressure. How much volume does it fill? And what we find is that relative to ideal gas, which should always be the same amount of volume per mole, 22.4 liters per mole, at constant pressure and temperature, we see that some gases deviate positively and some negatively. And in fact, for CO2, in fact, it's so significant that even in an atmosphere, we have a disagreement around the percent. Now, you may argue that, hey, 1% is not very much. That's a pretty good approximation for such a simple equation, and that's 100% correct. This is the easiest thing in the world, Pittman. So we do pretty good for this simple approximation. But we'll see that 1% makes a big difference when you're looking at things in a macroscopic lens. And if you're off by 1% per mole, for every mole that you have, your prediction of what you think its density or its molar volume is off by 1%. What if you're doing a process that over some sort of industrial process over the course of a year where you're processing millions of moles? We'll look at an example of the commercial production of ammonia.
No, 1% is 100.
Well, 1% is a mass, it's 100 millions of moles and millions of dollars of basically, if you've set your production facility up to assume a certain amount of CO2 coming in, and we'll see that CO2 plays a role in the formation of ammonia industrially. You have some, if you're off by 1% about how much ammonia or how much CO2 comes in, you're off by 1% somewhere else in your equilibrium process. You're doing that millions and millions of times, that amount propagates and accumulates significantly. It can cost millions of dollars. A really, really good example of this kind of enterprise level thinking. Now, I'm not a businessman. In fact, I've never worked a real job in my life, so what do I know? But a really good example of where these small differences can really accumulate on the aggregate as a kind of global scale is in the airline industry, where tiny, tiny changes of pounds on the plane can cost millions of dollars in differences. A really good example are the magazines that they stick in the back of the seats. American Airlines, I read an article, that was probably about 10 years ago, and airlines are always trying to cut costs. And the way they cut costs are by changing tiny little things across the entire fleet. And so you think about that SkyMall catalog in the back of an American plane or a Delta plane.
Right, they just take one page off of it.
Well, it's a little more obvious. They don't take one page, but you got the idea, right? It only weighs half a pound, third of a pound, but there's one for every seat on every plane. So over the aggregate, you're saving on the order of, let's say, 100 pounds a plane, and then millions of pounds across multiple planes in your fleet. And it turns out that the fuel savings from just removing that catalog is in the millions of dollars. You can save millions of dollars in gas that was through the catalog. That's why they're so anal about the size of your luggage, because the pound difference in everybody's luggage is millions and millions of dollars in lost costs. Right? So they're always nickel and diming these little percentages because they don't matter when you're working in the lab here. You've got a thing of CO2 in your PChem lab. Who cares if it's off by 1%? But if you're working with millions and millions and millions of liters of it, 1% is a massive difference. Okay, so this is where Pivnert, in some sense, fails. Is that it accumulates enough error that on the aggregate scale, it can be a real problem, especially when you're doing industrial processes. So we have to correct for it. But this is a PChem class, it's not an industrial class. I want to understand the bigger thing about the PChem is I want to understand why these gases deviate. And more importantly, why do they deviate differently? And the important distinction here that I showed was looking at different gases at high pressure. And we see that again, ammonia and helium or hydrogen, for instance, deviate in a positive way, meaning you have more, in some sense, you have more pressure in your system at a given temperature than you would expect. Meaning the gas is pressing against the walls harder than you would expect. Whereas there are regions where ammonia is quite attractive, right, where it's negative. So there are some gases that are all positive deviation at high pressure. There are some that are negative and then positive. And you can imagine that I can make this molecule more excessive, something more with oxygens, as polar, that these deviations become even more excessive. And so I want to understand today, we're getting to understand what's the source of these things. And again, the hypothesis is the intermolecular interactions between molecules in the gas. And we need to resolve two different observations. One is that it seems that the chemical character of the gas matters, or the molecules matter, and also the temperature at which they're at matters. The important thing here is that the deviations seem to go more extreme the colder we get, as if the heat just kind of washes out the effect. And you can imagine as I go from 200 to 300 to 600, say to 1,000, that this deviation just starts to slowly flatten. Eventually I get so hot that it would just look like an ideal gas. Okay, so we have to understand why that happens, right? Why is it a temperature sensitive thing? And so we have a chemical dependence, molecular dependence, and we have thermal dependence that we have to consider. Right? And these are hand in hand together. There's something that's unique to the molecule, and then there's something that's unique to the temperature that we'll have to consider together. And the way that we looked at this, again, I wanted to accentuate that interactions are inherent. And the inherent interactions that all molecules, all atoms have are actually attractive by and large. And the example I showed you was the Casimir effect, right? We take two boring metal plates and we bring them close enough together, they attract each other, regardless of any charges or dipoles or anything, like completely neutralized. Get these plates to attract, right? And this is what's called the Casimir effect. You guys have known the Casimir effect under a different name. It's called the van der Waals force, van der Waals effect in chemistry. And we'll explore that today. But before I did that, I wanted to introduce from a chemical perspective the interactions that we see. There are kind of four common classes of interactions we see in molecules. And we talked about two last class that are very straightforward, things that make a lot of sense, I think, if you think of physics or just general chemistry. The idea of an electrostatic interaction, that opposite charges attract. So that molecules that have dipoles, for instance, they have a negative end and a positive end in some sense. And the positive ends of one molecule attracts the negatives of the other. And so acetonitrile molecules tend to line up, or say like HCl, for instance, that's a good example. Hydrochloric acid molecules, they line up end to end like this, like a chain. Because the negative charge is on the chlorine or the CN, the positive charge is on the carbon or the H. So they just naturally line up like a line of dipole. And that's a very strong effect. It's long distance. It decays fairly quickly, but because it's proportional to the dipoles of the molecule squared, if you've got big polar molecules, it's a really, really strong effect. We'll see that. Right, so with polar molecules, this is largely the driving force for attractions. Water, for instance, formic acid, carboxylic acids, things like that. Those interactions and those molecules tend to be associated with electrostatic effects. Right, but you can all, and another kind of really obvious continuation of the dipole-dipole interaction is ion-ion. If you have ions that really truly have positive and negative charges interacting, it's very clear they want to be close together. That's a really, really strong interaction. It goes 1 over r cubed. So it decays much more slowly than dipole-dipole. Right? So if you go double the distance, this decays as 2 to the 6, which is like what, 64, 32, so 32 times weaker. And here it goes as 2 to the 3, which is 8 times weaker, right? So this decays at double the distance. This is 4 times weaker than this, or 8 times weaker. 8 times weaker. So ion-ion interactions are extremely, extremely strong, right? They're the strongest of any of the interactions in chemistry, which is why ions tend to associate very readily and are hard to break apart. And you can think of, we'll see that this is indicative of thermodynamic properties. When we start thinking about solids, for instance, melting temperatures, melting will have something to do with the strength that things hold together. And it's very hard to melt sodium chloride ions. Right? If you have a sodium chloride crystal, its melting point to make molten salt is very, very high, even though it's only 2 atoms. But because they're bound so strongly, you really have to pump a lot of heat into it to break the solid, the crystal. Whereas acetonitrile, you know, it's a room temperature, it's a liquid, and it melts at like -20 or something. It's very easy to break the crystal in solid dipoles because they just aren't bound as strongly at normal distances compared to ions. And so there's some thermodynamic conclusions that we can make about these. Perhaps a little more subtle is the idea of induction. which is the idea that you have a charge somewhere, say a dipole or an ion, that when you bring in something else that has an electronic distribution, that it induces a dipole in that other object. So an example here I've given is the interaction between nitrogen gas and acetonitrile. Nitrogen itself has no dipole moment. It's a nonpolar molecule. And we saw in the plots that nitrogen gas is repulsive, right? It doesn't really attract itself at 300 Kelvin. There's not a lot of interactions between nitrogen and itself, as we'll see, because it doesn't have a dipole moment. But if you bring it in the presence of a dipole moment or something polar, like acetonitrile, the presence of that charge distribution, that asymmetry in acetonitrile, induces a motion in the electrons of the nitrogen to kind of move. Right? So if you've got a lot of negative buildup here, nitrogen coming in this way, the nitrogen's electrons are going to want to move further away from the nitrile in this direction, right? So you're going to induce a dipole in this direction in nitrogen in the presence of acetonitrile. So we call those induced dipoles. They're quite a bit weaker. They're R to the 6 as well, and they're only proportional to one of the dipoles because the other one doesn't have one. So they're naturally quite a bit weaker. Right? But they can happen, right? And this is why, even though we often consider nitrogen, for instance, to be an inert gas, it doesn't do a lot. If you ask a chemical physicist, someone like me, about how we feel about nitrogen, we would say it's slightly sticky. It's a sticky gas. And that's not because it's reactive or it's actually viscous, like a sticky solid, like a liquid. It's not that at all. It's just that because of its polarizability, because you can induce a dipole in it, it has some interactions with molecules. It's a little sticky. It's not just like a helium atom that just bounces around like an idiot. It has some information. It has some affinity to polar things. So it's just slightly sticky. Okay? And so induction causes stickiness to things that would otherwise not be polar. So the other two that we haven't introduced yet are more subtle, much more subtle. They're just as important. They're weaker, but they're more subtle than dipole or induction. Right? These are in some sense just kind of what you learn in electrostatics when you take physics, right? The opposite charges are attractive and the same charges repel. Because all of this is taught. Well, what about attractions between things that don't have dipole moments or aren't polarizable? Things that are in some sense not sticky at all.
Can we talk about covalent bonds?
No, because that's not an intermolecular interaction. That's an intramolecular.
Oh, right. Okay.
Next semester, we'll talk about bonds.
What about a hydrogen bond?
Oh, let's talk about, actually, we'll come back to that. Let's finish up the 4, and then we talk about hydrogen bonds in the context of all 4. It's a great example. Yeah, where does a hydrogen bond exist? Right? Where does it fall into these categories? Good question. I'll answer that to you, I promise. We'll see hydrogen bonds are a special type of interaction that can be described by the 4 classes we're talking about. So the third one I want to talk about, the last attractive force, is what has many different names. Right? You'll often, there are, so the last one's repulsive. So the next attractive one is a force we call dispersion. There's lots of different terms for it. You'll often hear it called dispersion from me. Many chemists will call it the van der Waals force. And chemists or physicists call it the Casimir force. Right? We've already talked about that. Right? This magical force that 2 neutral objects feel against each other at close range. So just 3 different names for the same thing that come from 3 different people.
Still think it's crazy that was like proven in the 90s.
In the 90s, yes. In fact, I found the paper. I'll show it to you, and we'll look at it in just a minute.
Isn't gravity one of these?
No.
An example of this?
No. So here's an interesting question. Does anyone know the relative strength between gravity and the electromagnetic force? You happen
A
to know?
lot.
It's a lot. So does anyone remember roughly what the value of the gravitational constant was?
9 point something.
So
8
that's
point something.
that's the gravitation due to acceleration, but the gravitational constant, G. Does anyone remember that number? That was a long time ago. I don't even remember it. It's tiny, right? So let's go look it up. So I think this is an important answer. So this is an important question. Why doesn't gravity matter here?
It's 6.6743 times 10 to the negative 11 meters cubed.
Right.
Kilograms.
Thank you.
negative 1. It's like 2.
So in SI units, it's on the order of 10 to the minus 11. And so when you have two bodies, you could say, and so then you compare it to the electromagnetic interaction. There's another constant called the fine structure constant, which is the equivalent of G, right? G tells you how much force is exerted between two masses of a kilogram separated by a v. It tells you it converts between mass and distance to force for gravity, right? So there's also a constant called the fine structure constant, which explains how much force is generated between two charges separated at a meter. Right? So it's the same idea of electromagnetic force. This is 10 to the minus 11 in these units. In the units of electromagnetism, it's around 10 to the minus 46. And we have to get rid of a couple, do some conversions and stuff. It's around 10 to the minus 45 in electromagnetic units. The value of the fine structure constant in electromagnetic units is 1 over 136. It's about 10 to the minus 12. So the electromagnetic force at the scale in which it interacts is about 40 orders of magnitude stronger than gravity. So we don't care about gravity at all. Gravity has no effect on anything microscopic, period. You will never consider gravity because it literally has no effect. It's 10 to the 40 times weaker than electromagnetic.
Does that come down to like things having more mass? Like
no one knows the answer to that question.
okay, that's fun.
So the values of those constants, why the fact that they're 10 to the 40 difference is called the fine tuning problem. Why does the universe pick them to be so different? No one has an answer for that question. That's one of the unsolved problems in physics. So these numbers are measured, they're not derived. They're in some sense, they're input parameters for the universe. If you had a box that creates universes, they're the input parameters that you put in to create the universe. That's the way we look at them. So they're numbers that are a priori encoded into. Go ahead. What was your
Is it imagine trying to create a universe like simulating everything?
There is a group out of Argonne National Laboratory doing exactly that.
Really?
Yeah, on their giant supercomputer. Yes. Yes. Anyway, I digress. So, but it's a good question, right? Why do I consider gravity? Gravity does not matter. These are all electromagnetic forces. They're orders and orders and orders and orders of times stronger in magnitude than gravity. Gravity makes no difference. So we saw, I showed you that the Casimir force existed. I showed you an experiment that proves that it exists, but we don't really understand exactly the reason why it exists. Why did these two plates attract each other? And that turns out to be a very complicated thing to answer. I'm going to try to give it to you in a very simple kind of explanation. So let's go back to the plates. Right, imagine you have your two plates. Or they could be balls or anything, as I showed you before. I showed you they can be spheres. Anything attracts itself. So here's my two plates. Right, here's one of them. I'm just going to draw one for now. And imagine I have this. This is a metal plate, right? So the way we think of a metal is as a lattice. So there's columns and rows, and at each intersection there's a little atom. Okay, but over this lattice of atoms that are all stationary, these metal atoms, is what we call is what's called the Fermi sea. It's just this sea of electrons. So on the surface of a metal, it's just basically a roughly free-flowing sea of electrons. So you can imagine that you have all these complicated oscillations and waves and motion of all these electrons flowing on the surface. Okay, so on average, they're just moving randomly. So if I just have a neutral plate by itself, and if I were able to do this, turns out you're not able to do this, but if I could picture it, and I watch every electron move around, I would just see that they just move randomly, just like a gas, right? So each of those electrons, each of these little dots are electrons. All right, I'm just going to put a bunch. These are electrons, right? And they're moving randomly. Maybe some are stationary, some are moving really fast, some are moving in circles. So electrons move randomly. On metal surface. And then what happens when I bring in another surface of the same kind with random electrons, right? So now I'm going to bring in the other plate. New plate. All right, so I'm going to space the plate number 2 close to plate number 1, just like I do in the Casimir experiment.
You technically call that DX or TR,
Sure.
or like really small.
Yeah. Yeah, as the distance goes to 0. Not exactly to 0. So we'll talk about that. How close can they be where this breaks? So we'll have to think about that. So yeah, at let's say distances approaching atomic distances, right? So nanometer scale. What happens at nanometer scale? So here I bring in another plate at close distance. So here's my other plate. All right, so now I have 2 plates close together. Imagine some random motion happens in the yellow plate where the electrons move from the bottom to the top. Okay, imagine that there's a motion. All right, again, there's always random motions, and let's just imagine I'm waiting, and eventually I see some motion.
Wait, are we saying there's 3 plates?
There's 2 plates.
Yeah.
So we start with 1 plate, and then I'm bringing in the next one. All right, imagine I bring in this second plate here, really close by, right? And I notice that I just track a couple of motions on the yellow plate. And I just draw some very simple ones. I would say 2 go up this way, 2 go this way, 2 go this way. Right? And I want to ask the question, what's the response of the electrons on the other side?
The opposite.
Right, exactly. Right. So let's think about it this way. If you have 2 plates really close together, and the electrons are talking to each other. If 2 electrons want to move up, right, you have more of a charge distribution up here now. So the area of the plate, the opposite plate nearby, will want to be depleted in electrons, right? So if this is a negatively charged region, the equivalent part of the other plate wants to be positively charged. So you can kind of say we're building up, right? We're building up negative charge here and in the corners. And so the other plate is going to do the opposite. Right, we're going to notice that on average, the electrons in the other plate are going to move in the opposite directions. Right, so these electrons on this plate are going to move down. Right. These electrons will move up. And these electrons will move right. Right, so we see correlated motion between the electrons. Okay? That's exactly what it is. It's called electron correlation. This is a very weak effect, but this is general. Is that when you bring in 2 objects that have random electron motion, that when you bring them together, that the motions become correlated. That when one moves, fills negative charge in one space, that gets depleted in the other one. All right, so the presence of the second plate induces correlated motion of the electrons between the two plates. Right? And the scientific term for this, the chemists use for this motion, is literally called electron correlation. It's a, what's that? Yeah, that's right. Yeah, that's, who knows what the biology would call it. Electron pocket agonist or something like that. And so this is electron. This is true at when you have the interaction between two electronic materials, like the material containing electron, there's always a non-zero electron correlation. It's non-zero. It's always non-zero, regardless of, as long as it has electrons, it's always non-zero. This is a so no matter what distance the plate is, this value is always non-zero, right? The electrons are always correlated to each other. It may be so uncorrelated we don't even notice it, right? But it's always a non-zero value. And when you do the analysis of this math, right? So if you think about now the energy of these two plates, so that you initially start with them separate, where they're not interacting, and you bring them together, and you ask, what's the new energy of the plate combination? Right? Does the correlation add energy or lower energy? Is it destabilizing or stabilizing? And it turns out in 100% of the cases, or we'll talk about this in most cases, turns out it's a function of distance, but in the most stable region, the stable position between the two plates, they're not too close, not too far, it's always attractive. The correlation is attractive.
Question?
Yes.
What is the triple lines with the strike through it? Zero, but that's a zero.
Oh, sorry. It needs to be just
So
that.
it's about zero for any value.
It's non-zero.
Oh, non-zero.
Yes, and it's always attractive. Except at very close distances. All right, we'll talk about what kicks in at close distances. There's a new repulsive force that appears that's connected to electron correlation. All right, but we'll just say that reasonable, and what that means in terms of the plates is where the plates are literally on top of each other. All right, when the atoms of one start to impinge on the area of the atoms of the other, they start to repel. Right, well, I'll show you that in the next discussion about the next force. That's this repulsive force that appears. But barring that, just put two plates and they're reasonably far enough apart, they will always attract each other, non-zero amount. And that's due to the van der Waals force. Okay, this is chemically universal, materially universal. It's only dependent. All materials exhibit dispersion interactions. And it's dependent on two things. The number of electrons. So the more there are, the more attractive. A 5 electron atom will attract a 10 electron atom more than it will attract a 5 electron atom. And what we call the surface area of contact. All right, the more contact area, the stronger it is. That's why the plates are so attractive to each other, because there's lots of surface. Our phone books are a really great example of something that is very attractive to van der Waals forces are aromatic molecules, flat plane molecules, graphite, graphene, benzene, naphthalene. Things like that are very, very, very good acceptors of van der Waals forces. In fact, there's biochemical applications to that, as I'll try to explain to you today. Okay, and it's linear in both. More electrons, more surface area, the stronger the van der Waals force. How does it scale? Well, it's quite weak. Considerably weaker than the electrostatic force. So the force over area for van der Waals goes as 1 over r to the 12th. So remember that so this is r to the 6 faster decaying. Sorry, no, that's wrong. Sorry, I'm wrong. I got to go back to that. I apologize. It's the same. R to 6. It's as fast, same as the induced dipole. I was confusing it with another one. I apologize.
So it's as weak as the.
So it has the same length dependence. Same length dependence. But we'll see that it is weaker. But overall weaker. So you can kind of think of it like, if you think about interactions as waves, and you have two objects at the same distance and they create waves between each other. Waves are attractive. The frequency of the waves is the same regardless if it's an induced dipole interaction or a van der Waals interaction. Right? So the frequency of the waves are still the same. However, the amplitude of the waves are different. The dispersion amplitude is very, very weak. Think of it as little tiny oscillations like this. Whereas the electric field of an induced dipole is much larger oscillation. So it has a much larger multiplicative factor. So the multiplicative factor on the dispersion force is really, really tiny. So it's a really, really small wave, but it has the same frequency as the induced dipole wave. All right, we'll see that in just a minute. Okay, so those are our three attractive forces, right there. In some sense, there are two that are the same kind, like these ideas about dipoles and charges. And then there's this magical force, this van der Waals force, that's universal and much weaker. And we'll see that there's always a competition between the two, and it really depends on the molecule which one dominates. Pull out my notes. So I want to talk about the last one. The last one is a repulsive force. And it has no core, it has, in some sense, some relationship to electron correlation. But nothing to do with charges. A weird effect that only exists in microscopic regime. Right? I can't really give you you'll see in a minute. Can't really give you a picture of this force that you can connect to something you can touch and feel. It's unique to the microscopic world. And this is what's called exchange. Another term is it's named after the discoverer, Wolfgang Pauli. It's called Pauli repulsion. It's another term for it. Here's a very interesting observation. I'm going to go back to my two plates again. I'm going to bring this picture of my correlated plates again. And what I've described to you in this discussion was that when I bring one plate in next to the other one, it causes the electrons to move in opposite directions, right? To charge on one moves to one place and the other charge moves in the opposite way. That's attractive, right? So correlated motions are attractive, but there's something else electrons can do besides just move. So again, they can correlate their motion. This is weakly attracting. They can also swap positions. So when I bring my two plates together, these two electrons and these two electrons are the correlated pairs. and this drop. These move left, these move right. They have another option. The electrons on the orange can swap with the ones that are on the purple, what we call an exchange operation. Right? So I can also take this electron and swap it with this one or this one. Right? There's lots of different exchanges that I can do. And we call this exchange. Why am I allowed to do this? Why is this something I have to worry about? Well, electrons have a very unique property. And in fact, all microscopic particles, including atoms and molecules, have this property, but in electrons, it's particularly important. All electrons, or we'll say all microscopic particles of the same kind, are identical, meaning they're all the same. They all have the same masses. They all have the same charge. That's obvious. But even more, they are indistinguishable. What does that mean? What that means is that it is impossible for me to go in and mark these and number them and track them by numbers. So for instance, if I said, hey, this is electron 1, 2, 3, 4, 5, 6, right? I just number them. Then I would be able to, right? They all have names, they all have paths. And so I would be able to track them. Right? And that's what you would do with a billiard ball, right? This would just be like 20 different billiard balls, and they all have different names and labels. Easy to track them. Do not do that with an electron because electrons are by definition identical and indistinguishable. There is no difference between two electrons. In fact, there's so little difference between them, you can't tell them apart. If I pull an electron from this system, I just grab an electron. I don't know which one they come from. I take from both. I don't know which one it comes from. It comes from one of the two. And in fact, if I pluck one from here, there's a probability that, in fact, what happened was I touched this, and this one exchanged with one over here, and this purple one is now here, and I pulled that. Yeah.
So we don't know.
We have no idea. There's no way for me to distinguish between any of them. So what that means is that I'm free to make exchanges between them. There's a probability to make exchanges, and there's no preference for one electron to be on one end or the other. So because of this, exchanging electrons is allowed and dominates at close distances when atoms are very near each other. So as R goes to 0, as the distance goes to 0. So if I were to measure the distance between these two plates as L, right, as L goes to 0, this begins to dominate. And what Pauli shows that by definition, exchanges of identical electrons cost energy. All right, it doesn't give back energy like an attraction does. Therefore, it's repulsive. Right? So the system, in order for electrons to behave as an electron would, they have to, right? Remember when we talked about equilibration? A system has to explore all of its possible arrangements, all the different possible things it can do. And this is 100% true for electrons as well. And so electrons, in order to equilibrate, they have to explore all the different exchanges. And those exchanges cost energy. They're always there. They become stronger as two atoms of electrons get closer together. We'll talk about how important that becomes.
Like
but it costs energy.
Crisis.
Yeah, sort of. And so this is just one of the things electrons have to do in order to equilibrate, and it costs energy and therefore is repulsive. And so repulsions in electronic matter don't come fact, the only thing that it is in some senses, what it's telling you is you've come too close. If things are just able to sit at reasonable distances with each other, everything would attract everything. But there's in some sense, there's some final limit to how close you can bring things together, because when you bring them so close together, then the electrons begin to exchange more and more, and it drives them apart. It turns out that this is, interestingly enough, exchange is the reason why stars go supernova. Interesting observation. So it turns out that when you, here's another nerdy tale about things that are not related really to chemistry. But one of the things that happens when a star dies is as the star runs out of hydrogen and helium diffuse, it starts to fuse bigger and bigger atoms together. In order to facilitate the fusing of large atoms, you have to have a hotter core. In order to have a hotter core, you generate more by having a hotter core that fuses, say, carbon, nitrogen, and oxygen, big heavy atoms. Your core has to be hotter. Therefore, but you also generate more energy, more exothermic fusions in hydrogen. So what happens is that a star that's very large, when it runs out of hydrogen, it starts to fuse carbon, nitrogen, oxygen, heavier and heavier atoms, and it goes through a runaway cycle. It keeps pulling out more and more energy, gets hotter and hotter as it fuses through stuff, as it starts, and then because it gets hotter, it gets bigger. And because it's getting hotter, it starts to expend all of its material, right? So these stars start shedding material, and what's left in the core after it's exuded all of those atoms and all of that gas is a giant core of electrons at the bottom. Think like a giant molten metal core that's filled with electrons, super, super hot electrons. And this thing is getting larger and larger and larger as the star feeds itself. You get this bigger and bigger and denser core of electrons. And once the electrons get dense enough and heavy enough, the energy that it creates is greater than the gravitational strength of the star keeping it together, right? There's always a balance between gravity and the energy of the fusion reaction pushing out. So a star stays stable. Eventually, those electrons have so much exchange energy, they're so dense that the gravity can't contain it anymore and it blows up. Right? That's a supernova, type A supernovas. It comes from the fact, it's driven by the fact that what they call electron degeneracy energy, the energy caused by excessive exchange, becomes so great that it compensates over gravity when the star explodes. The sun will never do that. The sun's not heavy enough. You have to be the smallest possible star, if I remember correctly, 60% larger than the sun. So our sun will expand and grow, but eventually it will just shrink and die. It never gets enough energy and pressure in the center to explode. Eventually it will just burn out and fizzle out after consuming us. So one thing that will happen is once the star runs out, our sun runs out of hydrogen, start fusing the larger atoms, that will make it explode in size. It'll be to the point where the radius of the sun is past Mars. So all the inner planets will be consumed, and then eventually it'll run out of energy and shrink into a giant little tiny thing about the size of Jupiter. And then over the course of a million years, will burn out under that. So
That's so exciting.
I know, isn't that interesting? So that's really, really important, but only at big scales. Right? It's a really small effect, and it happens microscopically. But the only time it really affects things macroscopically, there are exceptions in chemistry, but the supernova is fueled by exchange energy, electron exchange. Now, as we'll learn next semester, there are certain types of particles that don't have this repulsion. Right? There are some particles that do have this exchange repulsion and some that don't. So that's not really a worry about this class right now. Okay, so those are our four forces. So let's put them all together and put them in context. All right, so let me show you some examples from the literature from my research. And again, Angie mentioned hydrogen bonding, so let's talk about hydrogen bonding. Right? What is a hydrogen bond? Well, I can actually pull up a program. I'm not going to show it to you, but there's a program where I can give it two molecules and arrange them at some position, and it will tell me the different interaction strengths that the two molecules have. Okay, we can actually calculate how much electrostatic, how much induction, how much dispersion, and how much exchange it has. Okay, so I'm going to look at. So let's just look at, for instance, at water dimer. Right, this is what we call a hydrogen bond. The classic hydrogen bond is dimer of water, right? And it has a nice structure. This is what water dimer looks like. Yeah, the hydrogen bond is this connection right here. Right, and let's just remember that again, we have a negative charge on the oxygen. Sorry. That's my fault. We're almost there. There we go. And we have a positive partial charge on the hydrogen. So again, this is a dipole and an induced dipole. There's a little bit of, as we'll see, there's a little bit of electrostatic in here, right? We have a dipole-dipole interaction here. But it also induces, it turns out it also induces the dipole as well in water. So there's also some induction. All right, so hydrogen bonds are stabilized by both. Let's look at how the energy balances out. How does the stabilization express itself? So I'm going to split the energy into four parts. One is the electrostatic energy. One is the induced energy from induction. One is the dispersion energy. And one is the exchange. All right, so those are our four energies. And then we can look at the total energy, which is just the sum. And then we'll look at it relative to experiment, right? These are calculations. So I'll write that here. These are calculated values. Right. The reason why they're calculated is because we can't actually measure these things in experiments. The only thing we can measure in experiment is this value right here, the total. So these are, in some sense, like they're not imaginary, but what we're doing is we're modeling the electrons of the system in such a way that allows us to compute these things. But to measure in an experiment is impossible. All we can measure is this right here. So this just gives us kind of a nice heuristic picture of how the energy is divvied up between the two molecules, the interaction. But really all we can measure is the strength of the interaction.
Wait, what's EXPT?
Experiment. Sorry, it needs, I'm missing an E here. There we go, is that better? This is experimental value. Right, and we can experimentally measure the binding energy, the strength of these intermolecular interactions. It's very easy to do. And the units I'm using here, right, so all of these units they're not in kilojoules, but they're written in kcals per mole. Which is equal to 1.484 kilojoules per mole. All right. Kcal is just 4 kilojoules. Does anyone know how this is interesting? If you're curious, again, kilocalorie is what you read on the back of your cereal box. And why we use, so for some reason theorists still use kilocalories, even though experimentalists use kilojoules now. And where kilocalories come from is the amount of energy to heat a mole of water by 1 degree. 1 gram of water by 1 degree. It takes 4.1 or a liter of water. So this is how much energy it takes. 1 kilocalorie per mole is how much energy it takes to heat 1 liter of water by 1 degree. And that's 4.184 kilojoules. So it's a water-based unit of energy. which is why we typically use it in conjunction with our thermodynamics, which are defined by water, right? Temperature, pressure, and our energy units are all water associated. So that's kind of a historical note. But occasionally I'll use kcals in this class. And just remember they're different by a factor of 4. So in water dimer, again, we would expect the electrostatic energy, the dipole-dipole interaction to dominate. And that's exactly the case. So the total binding energy electrostatic is minus 8.88 kcals per mole. This is dominantly a dipole-dipole interaction. We're going to get a lot of negative charge buildup in the oxygen, a lot of positive charge on hydrogen. And remember, we have this lone pair here that it's interacting with. The lone pair on the oxygen, that's a lot of charge. So the dipole-dipole interaction is really strong. And the induction is less strong. It's a very subtle point. But the thing that the hydrogen really interacts with is not the oxygen per se, but rather the lone pair on the oxygen. Right, that lone pair. And the thing about lone pairs is that lone pairs are, as we'll learn next semester, lone pairs don't really interact with the structure at all. They don't, that's why they're lone pairs. They're just a set of electrons by themselves. And so when I interact this negative charge in this lone pair with the H, it doesn't really affect the overall electronic field or the electric field or the electric potential of the water molecule with the lone pair, like the acceptor. Because this lone pair in some sense is like on its own. So it doesn't induce a strong dipole moment, but there is a little bit of induction. If, for instance, if we replace this with a different atom, say H2S, the induction would probably be a little stronger because there the lone pair mixes. It's complicated, but this is largely dipole-dipole. So when I look at the induction energy for this, it's a very, very small number comparatively, minus 2.15. Right, so it's dominantly a polar interaction, a classic electrostatic interaction between two bipoles. But there's always a little bit of dispersion. I said dispersion is not something you can get rid of. It's always there. It's about 1 kilojoule per mole. And then the exchange energy is a positive value again because it's a repulsive. And you can see that the exchange energy actually compensates for a lot of the stabilization. Almost all of the electrostatic energy is compensated for with the exchange energy. And so there's always this balance between repulsion and attraction. Just in the water dimer case, you have an accumulation of 2 of 3 significant stabilizing effects that all contribute to some amount. And they strengthen it overall relative to the exchange repulsion. And so the total value that you get out of this is minus 5.17 kilojoules. And I'll come back to the experimental number in just a second. I don't have them on my paper. They're in my thesis. I just need to pull up the page. I always forget to write them down. Just a sec, guys. Work archive, dissertation. Right. Know exactly where this slide is. Almost there. Lip, sapped. Theory. Here it is. Okay. And the lit value, yeah. The lit value is minus 5.02. Okay. So pretty good agreement, right? These calculations, by the way, they only took me about 30 seconds. So really, really simple calculation. And so they get me pretty close to the correct data. Again, remember, everything that we do in PChem, ultimately, we like to talk about real theory. What's the truth? But eventually we have to make approximations because we can't do everything at the highest precision. Sometimes we need to like graduate or go home or just publish a damn paper. So sometimes we have to make approximations, and there's a good reason for that. Sometimes it isn't necessary. Like, do we really care about that extra 0.1 kcals? Probably not. It turns out that there are other things, other errors in this calculation that are on the order of 0.1 that aren't being resolved here. So it's good enough. Okay, so that's the idea, right? So hydrogen bond truly is a primarily electrostatic interaction. Let's look at a slightly different hydrogen bond. This is a really, really common interaction. It's called a CH-pi interaction. And these are the forces that stabilize the inner part of the double helix of DNA. Maybe next class we'll look at DNA structure a little more carefully and look at how these different forces play a role in the structure of DNA. These are also really big in medicinal chemistry. These are major interactions, in particular in anesthesia. It turns out in most anesthetics, the way that they bind to their receptors are through these CH-pi interactions. When you pi interact with pi, you'll see it's just a double bond. Bonds and stuff. So like a benzene. So that's the example I'm going to use today. Is the benzene dimer, the dimer of benzene. And benzene dimer has a really cool structure. I'm going to kind of draw this benzene so it's kind of sticking out of the page a bit. Thickened out the front and then narrowed the back. And then above it, imagine I have it like a ring right here, like my flat palm. Above it, the other benzene is going to come in and insert a hydrogen into the center, like this. So directly above it is a hydrogen that's attached to another benzene ring. Right, benzene dimer. In fact, there was a long discussion when I was in grad school of whether this was the most stable structure or not. There was a conflict because some calculations would suggest that, in fact, this was not the most stable structure, but the most stable structure was called the slipped. Sorry.
So that hydrogen just coming off somewhere on the benzene.
Yeah, it's one hydrogen. So think of it like the ring. So you have the ring planes on my hands. Okay, and you've got one like this, and here's one of the hydrogens sticking off the other benzene. It's like this, coming directly into it, 90 degrees, like a right angle.
Okay. So I draw like.
Let me see if I have a pretty picture of it somewhere. For a long time, people thought that this wasn't the most stable structure. In fact, the structure that people thought, let's see if I can draw it, where the two rings kind of sat like two pancakes. Like this, on top of each other. On top of each other. So this is like a stacked. But it turns out that they proved in 2012, an experiment, that in fact the insertion complex, where the H inserts into it, is actually more stable. Right? It's very, very hard to compare the two. They're very similar in energy. And you actually see both of these interactions in biochemistry and proteins everywhere. But this is what's called a pi-pi interaction. The two rings together, because the two pi systems, two double bond systems of the ring are interacting forever. They sit together like two pieces of paper. Whereas this is a finger pointing into the donut instead of two donuts on top of each other. Okay. I'm sure you guys can think of something far cruder than that. I'm gonna stop. I have some really bad jokes in my head. Yeah, I'm gonna get canceled, so I'm gonna stop talking. So let's ask a question now about the different energy contributions of these structures. And I think I have, do I have data for both of them? I might only have data for one. I only have data for one. For the insertion one. Okay, so here's the interesting thing. Benzene doesn't have a dipole moment. Right? Because benzene has a hydrogen pointing out in all 6 directions. It all cancels out. Right? If you imagine that there's a lot of negative charge in the center, and the hydrogens are positively charged, that's a reasonable way to think about benzene. It's a little more complicated than that. But actually, you should think of benzene as like a donut of electrons. But in general, you could say that it's negatively charged and this is positively charged. And kind of the ring itself is negatively charged, right? So this is kind of like a dipole. In some sense, what you've done is this itself doesn't have a dipole, but it does have negative charge. You've induced the dipole perhaps, right? You're pulling on the electrons perpendicularly. Right? And you've put this benzene in a position that relative to this, it has a dipole. It's hard to explain, but basically I've broken the 6-fold symmetry of the ring because this hydrogen is now different than all the other ones. This hydrogen is more positively charged than the other ones. So now I've induced a dipole moment in this molecule. All right, so this has a dipole.
Induced dipole.
Yes, but it's permanent. But it also does induce some induction as you bring in the other ring. Right, because it draws electrons into the center, right, from the exterior. Right, so there is a little bit of a
pointing inwards.
Correct. It's more of a current, if you would. It's rather there's a flow of electrons in this direction, and the presence of the yellow benzene ring induces an additional current. Kind of stirs the electrons up in the center. So that induces some electrostatic interaction. So we would expect to see some induction and some electrostatics, and we do. But it's much weaker. Right? It's almost 4 times weaker than the hydrogen bond electrostatic force in water. And the induction is much smaller again, because again, benzene is not as polarizable. It's a hydrocarbon. We know that hydrocarbons aren't polarizable, right? Because they're not, just think about them as solvents, right? Benzene doesn't solvate water. Water is very polarizable, it's very polar. Typically, light solvates light. Benzene does not solvate water. It's not a particularly polarized solvent, so there's not a lot of induction. But there is some, because we've associated this benzene in such a way that has induced dipole, right? By definition. It's got a hydrogen, kind of an asymmetry between the hydrogen and the ring, instead of the ring and the ring, which is why it's more stable. Not surprisingly, the thing that dominates here, we have these big fat rings, lots of electrons in them. The dispersion is much stronger than any of the other forces by a factor of 2. Right, we got 2 fat rings. So large surface area. And lots of electrons. Okay, so lots of dispersion. It's largely dispersion. But unfortunately, the dispersion force doesn't really matter because it's almost entirely canceled out by the exchange. You see that, we'll see this a lot. And we'll look at another example that's even more dispersion oriented. That the system is stabilized by dispersion quite a bit. And what happens is, in order to maximize the electrostatic interaction, it really wants to bring things in close. because charges like to be close to each other. But as you bring the charges close together, the exchange increases as well. So you always have a trade-off. Exchange goes up as electrostatic goes down. And so you have to find a balance. And when you find that balance in the system, it almost negates all of the dispersion. So even though that these two things are always attracted to each other, we get them in the right position, it just works out that the exchange energy basically negates all the dispersion. This is why dispersion is always very weak, especially in systems like this that don't have like fluorines and polar atoms, hydrocarbons, is that they are attracted to it themselves, but they also like to exchange electrons, and they negate each other quite often. So overall, this doesn't bind very strongly. Right, it's about half the strength of water dimer, but it agrees very, very nicely with experiment, right, which is only off by a couple hundredths of a K count. Done? 4:45 there. Okay, so we're just about finished. Okay. Do we have enough time for one more? No, probably not. Okay, so I've given you a gist. So we'll finish up a couple more examples on Thursday. I want to show you a pure dispersion example. And then I want to talk a little bit about this balance between dispersion and exchange. It seems like they're somewhat correlated. As one goes down, the other one goes up. And we're going to see that time and time again. What we'll learn is it's a function of distance, a distance-dependent parameter. And we'll talk about how we model these two distances, right? And when we talk about that model, it's going to give us a way to start thinking about how do boring-ass noble gas atoms, helium, argon, nitrogen, things that don't have any of these interesting things, how are they non-ideal? And we're going to see that if we model their exchange and their dispersion alone, don't worry about the electrostatics, we'll be able to come up with a model for a gas that gets us really, really close to the correct answer. And that's the van der Waals model from homework 1. All right, so homework 1 will get us to the position where we can understand these two exchanges, these two parameters energetically, and that will give us a model for a non-ideal gas that's close to reality. All right, so we'll derive that expression next class. We'll talk about the van der Waals gas, finish this up, and then we'll see the consequences of the van der Waals gas from there. All right, have a good one, guys.
Thank you.
Thank you.
I'll see you tomorrow. Thank you. Have a good day.
Guys. See you Thursday.
Always, I message them. Ask you a question.